Hello everyone, welcome to our new lecture. In today's lecture, we are talking about matchings. A matching in a graph G is a set of edges, any two of which do not share a vertex. There are 4 sections in this lecture. The first part is about matchings. The second part is about cover. A matching in a graph is a set of edges with no shared endpoints, and a cover of a graph is a set of vertices such that it contains at least one endpoint of every edge. The third part is about real-world applications of matchings. And the last part is Hall's theorem, which is an important theorem in graph theory. This is the definition of a matching. A set of edges M, which is a subset of EG, in a graph G is called a matching if the following condition is satisfied. For any pair of edges E prime belonging to M, E intersection E prime equals empty set. That is, the edges in a matching are vertex disjoint. Any two of the edges do not share a common vertex. Here is a graph with 8 vertices. We can choose an edge from this graph, 0, 3. This single edge, 0, 3, forms a matching. If we choose another edge, 2, 4, from the graph, the two edges, 0, 3 and 2, 4, also form a matching. This is because 0, 3 and 2, 4 do not share a common endpoint. They are a set of disjoint edges, which forms a matching. If we add another edge, 4, 6, the set of edges 0, 3, 2, 4, 4, 6 is not a matching, because 2, 4 and 4, 6 share a common vertex 4, which contradicts the definition of matching. Also, note that a matching does not contain a loop. So any set of edges, including this loop 6, 6, is not a matching. The upper right graph shows a trivial matching. This is a trivial matching because it's a matching which contains 0 edges. The lower left graph shows a maximal matching. The edges 1, 3 and 4, 6 form a matching which is maximal because you cannot obtain a larger matching by adding edges. If you add any edge to this matching, it is no longer a matching. The lower right graph shows a maximum matching. The edges 0, 3, 1, 2, 4, 6 form a matching which is maximum and maximal because you cannot obtain a larger matching with more than 3 edges in this graph. This is not the only maximum matching. We can find another maximum matching. For instance, the edges 0, 1, 2, 4, 3, 5 These three edges also form a maximum matching. The second definition is about perfect matching. A matching is perfect if the size of M equals half of the order of G. That is, it covers all vertices of G. This graph is a cubic graph of order 8. The red edges form a perfect matching of this graph. So in a perfect matching, every vertex of the graph is incident to exactly one edge of the matching. A perfect matching is therefore a matching containing half of n edges, which is the largest possible. Meaning perfect matchings are only possible on graphs with an even number of vertices. This is because in a matching, one edge covers two vertices, two edges cover four vertices, m edges cover 2m vertices. A graph with an odd number of vertices cannot contain a perfect matching. The graphs below are cubic graphs of order 8. The red edges form a perfect matching of this graph. This graph has 9 perfect matchings. We denote the size of the maximum matching in G by nu G. The following figure shows examples of maximum matching in 3 graphs. This red edge forms a maximum matching of this graph. That is to say, if you add any edge to this matching, it is no longer a matching. The following figure shows examples of maximum matchings in the same 3 graphs. So this one red edge forms a matching, but is not a maximum matching. We can find a maximum matching with 2 edges in the same graph. For the same reason, these 2 edges is a maximum matching but not a maximum matching. We can find a maximum matching with 3 edges. Note that a maximum matching must be a maximal matching. The third matching is both maximal and maximum. Here you must remember that the size of the maximum matching in G is nu G. Now we calculate the size of a maximum matching in some special graphs. In the complete graph Kn, if n is even, then it has a perfect matching. If n is odd, then it has a matching covering n minus 1 vertices. For instance, in this graph K7, we can find a matching with 3 edges. So the size of a maximum matching in a complete graph is floor of half of n. In the complete bipartite graph KST, here S is less than or equal to T. Since every edge has one vertex in this part, so a matching contains at most S edges. we can find such a matching covering every vertex of this part. This is a maximum matching. Thus, nu KST equals S. When G is the Peterson graph, we can find a perfect matching. This is a matching covering every vertex. So when G is a Peterson graph, nu G equals 5. We have the following remarks. We have mentioned that a matching contains no loops. A matching in a graph G corresponds to an independent site in the line graph LG. Because in the line graph LG, every vertex denotes an edge in G. If the edges in G have no common vertex, then for any two corresponding vertices in LG, there is no edge between them. The corresponding vertices form an independent site. If G has a perfect matching, then the order of G is even. But the reverse is not true. If the order of G is even, G may not have a perfect matching. Here are two examples. In the left graph, if it has a perfect matching, then the perfect matching must cover every vertex of this triangle. To cover every vertex of this triangle, we need two edges. This edge and this edge must be in the perfect matching. For the same reason, to cover every vertex of the second triangle, we need two edges. This edge and this edge must be in the triangle. For the same reason, to cover every vertex of the second triangle, we need this edge and this edge. These two edges must be in the perfect matching. But now we see that this is not a matching because these three edges share a common vertex. This graph has 10 vertices, but it has no perfect matching. In the red graph, if it has a perfect matching, to cover this vertex, we need this edge in the matching. And to cover this vertex, we need this edge in the matching. But now, it is no longer a perfect matching. It is no longer a matching because these two edges share a common vertex. So this graph has 6 vertices, but it has no perfect matching. Now we turn to the second section. Consider a vertex cover. A matching is a set of edges, and a cover is a set of vertices. A set of vertices, T, which is a subset of VG of a graph G, is called a cover of G if the following condition is satisfied. Every edge E belonging to EG intersects T. That is, if you delete T from G, then G minus T has no edges. It is an empty graph. In other words, a vertex cover of a graph is a set of vertices that include at least one endpoint of every edge. In the graph below, the two vertices in the middle, the two eyes, form a cover, because every edge has at least one endpoint as an eye in one of the eyes. In other words, if we delete the two eyes from this graph, the remaining graph has 4 vertices and no edge. The remaining graph is an empty graph. We have a notation tau G. We denote the size of the minimum cover in G by tau G. The following figure shows 2 examples of vertex covers marked in red. They are not minimal covers or minimum covers. Actually, the set of all vertices also forms a cover. We can define minimal covers, but here we pay more attention to minimum covers. The figure below shows examples of minimum covers in the previous graphs. If we delete these 2 red vertices in the left graph, the remaining graph is an empty graph. Moreover, we cannot find a cover which has a single vertex. So here, the 2 red vertices form a minimum cover, and tau G equals 2. In the right graph, if we delete these 3 red vertices, then the graph becomes an empty graph. Moreover, we cannot find a cover which has 2 vertices or less. So here, the 3 red vertices form a minimum cover, and tau G equals 3. Now we calculate the size of a minimum cover in some special graphs. In a complete graph Kn, if we delete n-2 vertices from Kn, there is still an edge in the remaining 2 vertices. So to get an empty graph, we need to delete at least n-1 vertices. Thus, tau Kn equals n-1. In the complete bipartite graph KST, here S is less than or equal to T. If we delete all the S vertices in the second part, it becomes an empty graph. But if we delete any S-1 vertices from the graph, there are still some vertices in both of the 2 parts, so it is still non-empty. So to get an empty graph, we need to delete all the vertices in one part. Thus, tau KST equals S if S is less than or equal to T. When G is a Peterson graph, the situation is a bit difficult. Actually, we can find 2 5 cycles in the Peterson graph. One inner C5 and one outer C5. The edges in the outer C5 do not incident to the vertices in the inner C5. Also, the edges in the inner C5 do not incident to the vertices in the outer C5. To cover the 5 edges of a 5 cycle, we need at least 3 vertices. 1, 2, 3. We need at least 3 vertices. Also, to cover the 5 edges in the inner C5, we need at least 3 vertices. So we need a total of 6 vertices to cover all the edges of the Peterson graph. Let me read this note again. Note that the graphs induced by the outer 5 vertices and inner 5 vertices are both 5 cycles C5. Since tau C5 equals 3, at least 3 of the outer vertices and 3 of the inner vertices must be included in a vertex cover. So for a Peterson graph, tau g equals 6. The 6 right vertices form a vertex cover of the Peterson graph. Here is a proposition telling us the relation between the size of the maximum matching, nu g, and the size of the minimum cover, tau g. The proposition is nu g is less than or equal to tau g less than or equal to 2 times nu g. Take the Peterson graph for an example. The Peterson graph has a perfect matching. So nu g equals 5. And any vertex cover has at least 6 vertices. Tau g equals 6. 6 is between 5 and 10. So this property holds for the Peterson graph. How to prove this proposition? Let M be a maximum matching in G. Since every cover has at least one vertex on each edge of M, and edges are disjoint, we have nu g is less than or equal to tau g. Otherwise, if nu g is greater than tau g, for example, nu g equals 5 and tau g equals 4, then the 4 vertices cannot cover all the edges of M, which contradicts the fact that it's a cover. Note also that since M is maximum, every edge E of G intersects some edge E prime of M. Every edge E intersects some edge E prime of M. Otherwise, we can get a larger matching. So the vertices covered by M form a cover for G. Hence, tau G is less than or equal to 2 times the size of M equals 2 times nu G. So for a maximum matching and a vertex cover, every edge in the maximum matching is incident to at least one vertex of the vertex cover. On the other hand, all the endpoints of M form a vertex cover. The third part of this lecture is about real-world applications of matchings. One real-life situation is about workers and machines. Suppose certain workers can operate certain machines, but only one at a time. This gives a bipartite graph between workers and machines. If we want to have many machines operating at the same time, we need a large matching in our bipartite graph. The next application is the molecular structure of a compound can be described by a graph. For certain kinds of hydrocarbon molecules, a perfect matching of this graph gives information about the location of its double bonds. Here, every vertex is incident to at most one double bond. So, all these double bonds form a matching. The next one is the stable marriage problem. The purpose of the stable marriage problem is to facilitate matchmaking between two sides of people. Given a list of potential matches among an equal number of brides and grooms, we hope everyone to be married to an agreeable match. Here in this graph, we cannot find a perfect matching because A wants number 1 and 3, C wants 2 and 3, D wants 1, 2, 3, and E wants 2. So in the neighborhood of the 4 people, we have only 3 presents. So we cannot find a perfect matching. The Gale-Shapley algorithm for efficiently computing a stable matching was worth the Nobel Prize in Economics in 2012. The fourth real-world application is on the Chinese postman problem. Algorithms to find large matchings are essential subroutines for solving optimization problems. The Chinese postman problem involves traveling every edge at least once, while as short a total distance as possible. This problem can be efficiently solved by first solving a set of shortest path problems, then solving a certain matching problem. Note that the Orlean tour is to travel every edge exactly once, and the Chinese postman problem is to travel every edge at least once, while as short a total distance as possible. Now we come to the final part, and also the most important part, Hall's theorem. It begins with a job application problem. There are 5 companies and 5 applicants. We hope every applicant can be assigned a suitable job. Since there is the same number of applicants as the same number of companies, a perfect matching should be possible. But in fact, there is no possible matching. Here's why. Focus on the choices made by companies A, C, and E. We see that the 3 companies only chose 2 applicants, Mandy and Ada. So obviously, one of the three companies will not be able to hire. From the example, we see that a necessary condition for every company can hire a suitable person is for any set of X companies, the set of applicants they choose must have a size at least X. We can prove that this necessary condition is also sufficient. This was shown by Hall in 1935. A bipartite graph G equals VE with bipartition V equals A union B. A is one part, B is the other part, has a matching covering A if and only if for any subset S of A, the size of the neighborhood of S is greater than or equal to the size of S. This is Hall's theorem. Let NS be the neighborhood of S. That is, NS is a set of vertices which are adjacent to some vertex in S. Now we have a bipartite graph. Can we find a matching covering X? The answer is we can. Here is a matching covering X. But if this bipartite graph has many vertices and many edges, it is difficult to find a matching covering X directly. Then we can use Hall's theorem. For every subset of X, we check its neighborhood. For example, X1, the neighborhood of X1 contains two vertices, Y1 and Y3. We can check every neighborhood of every subset. So we check all of them. And we see that the size of the neighborhood is always greater than or equal to the size of the subset. So by Hall's theorem, we can find a matching covering X. Here is another bipartite graph. Using Hall's condition, it's easy to say that there is no matching covering X. The reason is, let S be the set of X1, X2, and X4. Then NS contains two vertices. Y2 and Y5. The size of the neighborhood of S is less than the size of S, contradicting Hall's condition. So there is no matching covering X. Here is Hall's theorem. A bipartite graph G equals VE with bipartition V equals A union B. One part is A, the other part is B. Has a matching covering A if and only if the size of the neighborhood of S is greater than or equal to the size of S for any subset S of A. The necessity is obvious. If G has a matching covering A, then every vertex of S has a distinct neighbor. So the size of NIs is greater than or equal to the size of S. Or we can prove the necessity by contradiction. If for some subset S, the size of Nis is less than the size of S, then we cannot find a matching covering S, though there is no matching covering A, which is a contradiction. To show the other direction, to show the sufficiency, we apply induction on the size of A. Induction on the size of A. If the size of A is 1, there is only one element in A. The assertion is true. Now let the size of A be greater than or equal to 2, and assume that 1 is sufficient. The expression 1 is sufficient for the existence of a matching covering A when A is smaller. This is the induction hypothesis. Now we distinguish two cases. Case 1. If the size of neighborhood of S is greater than or equal to the size of S plus 1 for every non-empty proper subset S of A. Then we pick an edge AB of G and consider the graph G prime equals G minus A and B. G prime is obtained from G by deleting the vertices A and B. Do you know why we delete the vertices A and B from G? Because now the size of A is smaller and we can use the induction hypothesis. Then every non-empty subset S of A minus the vertex A satisfies the size of the neighborhood of S in G prime is greater than or equal to the size of the neighborhood of S in G minus 1. Minus 1 is because we need to delete the vertex B, which is greater than or equal to the size of S. This inequality is from the assumption. So, by the induction hypothesis, G prime contains a matching covering uppercase A minus the vertex A. So, how can we get a matching covering A? This matching, together with the edge AB, yields a new matching covering A in G. This is case A. This is case 1. In this case, we assume that for every non-empty proper subset S, the size of Nis is greater than the size of S. So, case 2 should be there exists a non-empty proper subset A prime such that the neighborhood of A prime is equal to the size of A. This is the second case. Suppose now that A has a non-empty proper subset A prime with the neighborhood B prime equals Na prime such that the size of A prime equals the size of B prime. because the size of A prime is less than the size of A, we can use the induction hypothesis. By the induction hypothesis, G prime, which is a graph formed from G by the vertices A prime and B prime, contains a matching covering A prime. But G minus G prime satisfies the condition as well. If not, for any size S, which is a subset of A minus A prime, with the neighborhood of S in the graph G minus G prime less than the size of S, we would have the size of the neighborhood of S union A prime equals the size of neighborhood of S in the graph G minus G prime plus the size of B prime. This is because the neighborhood of A prime is exactly B prime. B prime equals NA prime. It's less than the size of S union A prime. This is because the assumption, which is contradicts to our assumption. So G minus G prime satisfies the condition as well. Again, by induction, G minus G prime contains a matching of A minus A prime. Putting the two matchings together, we obtain a matching in G covering A. In this case, we divide the graph G into two smaller graphs, G prime and G minus G prime. In the two smaller graphs, we can use the induction hypothesis to find two matchings, A prime and A minus A prime. Then, putting the two matchings together, we obtain a new matching covering A. This is interesting. We cannot use the induction hypothesis on G, but we can use the induction hypothesis on a smaller graph G prime and also on the other part G minus G prime. So the proof is done. We have four corollaries from Hall's theorem. The first corollary gives a so-called defect version of Hall's theorem. If in a bipartite graph G equals A union B, E, AB are the two parts of this bipartite graph. If we have the size of Ni's is greater than or equal to the size of S minus D, for every size S of A and some fixed D belonging to N, then G contains a matching of cardinality A minus D. Here, different from Hall's theorem, we have a parameter D. If D equals 0, then it is Hall's theorem. If D is not 0, then it doesn't satisfy Hall's condition, but we can use this corollary. Let's take the left graph for an example. The set x1, x2, x3, x4 has 3 neighbors. We can check that for every set S of A, the size of NS is greater than or equal to the size of S minus 1. Thus, we can find a matching with cardinality A minus 1. So how to prove this corollary? We can add the new vertices in the part B and join each of them to all the vertices of A. Then this new graph satisfies Hall's condition. So we can find a matching covering A in this new graph. After deleting the vertices in the original graph G, we can find a matching with A minus D vertices. Here's the formal proof. Let's state the corollary again. If in a bipartite graph G equals A union B E, we have the size of NS is greater than or equal to the size of S minus D for every set S of A and some fixed D belonging to N. Then G contains a matching of cardinality the size of A minus D. The proof is we add D new vertices to B, joining each of them to all the vertices in A. Call this resulting graph G prime. Note that the new graph G prime has the size of the neighborhood of S in the new graph G prime is greater than or equal to the size of the neighborhood of S in the graph G plus D. Because we have D new vertices and we add each of them to all the vertices in A. And this is greater than or equal to the size of S minus D plus D. This inequality is from here. S minus D plus D equals S for any subset S of A. So by Hall's theorem, the new graph G prime contains a matching covering A. Because G prime has D more vertices than in G. So in this matching, at least A minus D edges must be edges of G. So G contains a matching of cardinality A minus D. The proof is done. The second corollary is about a regular bipartite graph. It says that a regular bipartite graph contains a perfect matching. If a bipartite graph G equals A union B E is K-regular with K greater than or equal to 1, then G has a perfect matching. Here, in this bipartite graph, every vertex has degree 3. From this corollary, we see that this graph has a perfect matching. Actually, we can draw a perfect matching here. So how to prove this theorem? Let's restate this corollary again. If a bipartite graph G equals A union BE is K-regular with K greater than or equal to 1, then G has a perfect matching. Now we have the proof. Because G is a bipartite graph, the number of edges is equal to the sum of the degrees of all the vertices in A. The number of edges also equals the sum of the degrees of all vertices in B. Because this is a regular graph, every vertex is of degree k. So sigma dx equals k times A, and sigma dy equals k times B. So we see that k times A equals k times B, and we have the size of A equals the size of B. Then it is enough to show that G contains a matching covering A. If G contains a matching covering A, that matching is a perfect matching. Now every set S, which is a subset of A, is joined to NS vertices by a total of ks edges. This is because every vertex is of degree k. And these are among the k times ns edges incident with ns. So these ks edges are in the k times ns edges. So we have k times s is less than or equal to k times ns. So G satisfies Hall's condition. For every subset S, we have the size of the neighborhood of S is greater than or equal to the size of S. So we can use Hall's theorem to prove that G contains a matching covering A, and because A equals B, that matching is a perfect matching. The proof is done. The third corollary is about a regular even graph. It says that every regular graph of positive even degree has a two-factor. A two-factor is a spanning two regular subgraph. In other words, it is a subgraph with n vertices, and every vertex has degree 2. So a cycle is a two-factor. A disjoint union of cycles is also a two-factor. So a two-factor is literally a disjoint union of cycles. This graph is K5, a regular even graph, because every vertex is of degree 4. We can find a two-factor here. 1, 2, 3, 4, 5, 1. This is a two-factor of K5. But how can we prove the theorem for every regular even graph? Also, take this K5 as an example. We can prove it this way. Consider the orientor in G equals K5 that successively visit these vertices 1, 2, 3, 1, 4, 2, 5, 4, 3, 5, 1. This is an Orion tour. We can find a new bipartite graph based on K5. The new bipartite graph has two parts, U and W, and each part has 5 vertices, 1, 2, 3, 4, 5. The edges between them are following the Orion tour. There is an edge 1, 2 on the tour, so we have an edge 1 in U to 2 in W. There is an edge 2, 3 on the tour, so we have an edge from 2 in U to 3 in W. There is an edge 3, 1 on the tour, so we have 3 from 3 to 1. There is an edge 1, 4 on the tour, so we have an edge from 1 to 4. There is an edge 2, 4, 2 on the tour, so we have an edge from 4 to 2. There is an edge 2, 5 on the tour, so we have an edge from 2 to 5. There is an 5, 4 on the tour, so we have the edge 5 to 4. There is an 4, 3 on the tour, so we have an edge from 4 in U to 3 in W. There is a 3, 5 on the tour, so we have an edge from 3 to 5. And there is a 5, 1 on the tour, so we have an edge from 5 to 1. This is how we obtain this bipartite graph. We see that this corresponding bipartite graph is a regular bipartite graph. So by the previous corollary, we can find a perfect matching on this graph. This perfect matching corresponds to a 2-factor of the original graph. Here is the formal proof. Let G be any connected 2K regular graph. We suppose that G is a connected 2K regular graph. Since it's 2K regular, so it's a regular graph with positive even degree. We have learned that if G is a connected even graph, then G contains an Orion tour. So we can define a new graph G prime based on this Orion tour by splitting every vertex V into 2 vertices, V minus and V plus. If an edge of the Orion tour goes from V to W, put an edge in G prime from V plus to W minus. So the edges in G and in G prime naturally correspond to each other. We put all the vertices V minus as a part and all the vertices V plus as another part. It's easy to see that G prime is bipartite. It is also K-regular. This is because G is a 2K regular graph. We need to go out of every vertex K times on the Orion tour. So by the previous corollary, this K-regular bipartite graph contains a perfect matching. Now we collapsing each pair of vertices V minus V plus back into a single vertex V. So a perfect matching of G prime corresponds to a 2-factor of G. Each vertex V is incident to one edge which was incident to V plus in G prime, and that edge incident to V minus in G prime. Again, let's take this K5 as an example. If we can find a perfect matching in the bipartite graph, this matching has 5 edges: 1, 2, 2, 5, 3, 1, 4, 3, 5, 4. So from this perfect matching, we can get a 2-factor in the original graph from 1 to 2, 2 to 5, 5 to 4, 4 to 3, 3 to 1. This 2-factor is obtained from this perfect matching. We have a remark says that a 2-factor is literally a disjoint union of cycles covering all the vertices of a graph. A 2-factor is a disjoint union of cycles covering all the vertices of a graph. The final corollary is about system of distinct representatives. A system of distinct representatives, which is referred to as SDR. Its definition is: let A1, A2 to AN be a collection of sets. A family, lowercase a1, a2 up to an, is called a system of distinct representatives if all the AI are distinct and lowercase ai belongs to uppercase AI for all I. So an SDR has 2 conditions. The first condition is all the AI are distinct. The second condition is for all I, we have lowercase ai denotes the uppercase AI. Lowercase ai represents uppercase AI. Here is an example. We have 3 sides: M1, M2, and M3. We can use X1, X4, and X5 as an SDR of M1, M2, M3 because X1, X4, X5 are distinct and X1 is in M1, X4 is in M2, and X5 is in M3. So this is an SDR. Also, we can use X4, X2, X7 as an SDR because S4, S2, S7 are distinct and X4 belongs to M1, X2 belongs to M2, X7 belongs to M3. So the definition is super easy. We need 2 conditions. All the elements of SDR are distinct and every element represents a site. Here is the corollary of SDR. A collection A1, A2 to AN has an SDR if and only if for all I which is contained in N. Here N is a site with elements 1, 2, 3 up to N. And uppercase I is a subset of N. We have the size of the union of AI, where I belongs to the uppercase I, is greater than or equal to the size of I. How to prove this corollary? We first give an example. Let A1 equals x1, x2, x6, A2 equals x2, x4, A3 equals x1, x6, A4 equals x2, x5, A5 equals x4, x7. To find an SDR of this collection, we need to construct a bipartite graph. So how to construct it? It's like this. Because there are 5 collections, n equals 5. So first we have one part with 5 vertices. They are 1, 2, 3, 4, 5 respectively. And the union of AI is the other part. It has 7 elements from x1 to x7. x1, x2, x3, x4, x5, x6, x7. We see that A1 has 3 elements, x1, x2, and x6. So we join the vertex 1 to x1, x2, and x6. x1, x2, x6. A2 has 2 elements, x2 and x4. So we join the element 2 to x2 and x4. A3 has 2 elements, x1 and x6. So we join 3 to x1 and x6. A4 has 2 elements, x2, x5. So we join the number 4 to x2, x5. A5 has 2 elements, x4, x7. So we join x5 to x4 and x7. Sorry, there is no x3 in any AI, so we need to delete x3. We need to delete x3. So this is a bipartite graph with one part n elements 1, 2, 3, 4, 5. The other part is the union of the elements x1, x2, x4, x5, x6, x7. To find an SDR is to find 5 distinct elements, and each element represents a site AI. So this collection has an SDR if and only if this bipartite graph has a matching covering 1, 2, 3, 4, 5, covering this part. And the condition is for all I, the size of I is less than or equal to the size of the union of AI, where I is in the uppercase I. This is literally the Hall's condition. So the proof is done. Now let's see the formal proof. Define a bipartite graph with paths A equals n. A has n elements 1, 2, 3 up to n, and x equals the union of AI, all the elements in some AI, and all the union of them, such that IA is an edge if and only if A belongs to AI. A matching of n, a matching covering n in this graph corresponds exactly to an SDR, where an edge IA in the matching means that AI equals A. But the condition, the size of the union of AI is greater than or equal to the size of I. Sorry, here I should be uppercase. It should be an uppercase I. Is precisely Hall's condition for the existence of a matching covering A. So Hall's theorem provides the desired equivalence. Our proof is done. Thanks for watching this video. See you next time.